Okay, let's continue on with Graham's law. So in 1846, Graham discovered and uses this rate of effusion. So let's go back and talk about effusion just quickly. Effusion was that escape of gas molecules through a tiny hole, and that's just those gas particles will then just be moving into some evacuated space. So we said before that lighter gases are going to be able to effuse at a faster rate than more massive gases. So in 1846, Graham discovers that the effusion rate is inversely proportional to the square root of molar mass. So for example, remember we said that for our formula, remember we said that there was a typo here. So my effusion rate of one gas in comparison to another is going to be equal to the square root of the molar mass of the second one divided by the square root of the molar mass of the first one. So they're inverse there. So it should be 1 over 2 here and then 2 over 1 on that side. So let's do an example of this, maybe see what a kind of problem would look like for Graham's law. It says an unknown gas composed of homonuclear diatomic molecules, so same molecule, effuses at a rate that, or same atom, effuses at a rate that is 0.355 times the rate at which oxygen gas effuses at the same temperature. Calculate the molar mass of the unknown. So if I wanted to calculate the mass of the unknown, I'm going to use Graham's law because I am comparing a rate, and I'm going to compare that rate with molar mass. So I set that up here. So here's Graham's law. I'm going to write that first. And I know that the rate of this unknown substance, so I call that unknown X, over the rate of oxygen gas is 0.355. So all of this I'm just saying is 0.355. That's going to equal the square root of the molar mass of oxygen over the square root of the molar mass of the unknown. So I just plugged in here the molar mass of O2 and just brought this rate down. If I want to get rid of this square root because my goal is to get mx, I'm just going to square both sides. Okay, so I'll have 0.355 squared. That's going to equal 32 grams per mole over mx. Okay, so now if I did 0.355 squared, the 0.126 equals 32.0 grams per mole over m sub x. So then if I multiply this by m sub x and then take 32 divided by 0.126, then I would get my molar mass of my unknown. So if I do that, the molar mass of the unknown should be 254 grams per mole. Okay, perfect. So all they asked me to do was to find this molar mass using Graham's law, and that's what we did. Okay, so with effusion, if we're comparing helium versus argon, so the difference in the rates of effusion for helium and nitrogen, for example, will explain why a helium balloon would deflate faster. Anytime that I'm comparing a heavier gas with a more massive gas, we already said that with effusion, because the particles are going to be smaller in mass or in size, then a gas that is smaller in weight is going to be able to effuse faster. So in this case, it says nitrogen, but it should say argon. So I have helium and argon. So a helium balloon is deflating much faster here after a specific amount of time than argon is. And that's because helium atoms are so much lighter, they're able to effuse much more quickly. Diffusion, let's talk about that. So diffusion is the spreading of one substance throughout a space or throughout another medium or a second substance. So if I'm in the kitchen and I'm baking cookies, then my husband's in the living room and he'll smell the gas molecules of that amazing smell maybe like 20 or 30 minutes into me baking these cookies. So diffusion, just spreading it out through a specific amount of space. So although diffusion is faster for lower mass molecules, molecular collisions are what's going to make diffusion a lot more complicated. So the diffusion rate of gases throughout a volume of space is much slower than molecular speeds. And this is due to molecular collisions. So it takes a long time for diffusion to happen just because in the process of diffusion, we're having a lot more collisions, okay? So collisions occur because real gas molecules do have finite volumes. So in real world, it takes a lot of time for diffusion to happen. Because of the collisions, the direction of motion is constantly changing. So therefore, the diffusion of a molecule from one point to another consists of many short straight line segments. So it may take a while for us to get that sense of smell if I'm in the kitchen making cookies, because all of those particles are moving constantly and randomly, but it may take a really long time to get from the start point to this end point over here. So ultimately, we care about that net distance that's traveled, so we're kind of thinking about this maybe as like a state function, but the only difference is that in diffusion, even though I don't necessarily care about path, we just need to know that it takes a long time. So, real gases. Let's compare the difference between a real gas and an ideal gas. So we said that an ideal gas has to be something that will follow the ideal gas law, and it is also something that will follow those 5 assumptions to the kinetic molecular theory. Real gases will conform to the ideal gas equation at relatively high temperatures and relatively low pressures. So you need to highlight this or star this because this is something that's a possible multiple choice question. So in this graph here, we kind of zoomed in right here on this particular one at 1 mole. So this is where PV in is equal to PV over RT. So on the y-axis, I'm graphing moles. On the x-axis, I'm graphing pressure. At 1 mole, and I can see in between the 0 and 1 atmosphere of pressure, all of these gases, so I have nitrogen, I have methane, I have hydrogen, and then I have carbon dioxide. But I see that all 4 of them at 1 atmosphere are on an even playing field here. And they're not too far off, and there's not a whole lot of deviation from ideal gas at 2 atmospheres. So at really low pressure, all of these gases will conform as being an ideal gas. They will follow that ideal gas law equation. But if I follow the graph at high pressures and at a different number of moles here other than 1, as I'm increasing in my mole count here, then I can see that they're going to deviate from this ideal gas. They're also going to deviate at a certain point here, especially CO2. So real gases conform to ideal gases if they're relatively high in temperature and low in pressure. I can say this in a different way, okay? So, and let's see how I could say this in a different way. Even the same gas will show wildly different behavior under high pressure at different temperatures. So ideal gas behavior doesn't just depend on pressure, but it's also going to depend on temperature. As the temperature increases, the behavior of a real gas is going to try to approach that of an ideal gas. So I can see here, if I'm just talking about the exact same gas, so I'm looking at the same sample, at 200 Kelvin, I see that it's going to deviate a lot at high pressure and at a low temperature from an ideal gas. As I increase that temperature of the same gas, then it deviates there's not too much of a difference, but it's deviating less from an ideal gas. As I increase that temperature even more so, then I'm really close to getting to that ideal gas situation. So what are the deviations for real gases? A deviation from ideal behavior will happen at high pressure and at low temperature. A deviation from ideal gas behavior will happen at high pressure and low temperature. I think we should repeat that maybe just one more time. Deviations from ideal gas behavior will deviate at high pressure and low temperature, okay? So if we focus on... Guys, Mrs. Eldridge just wanted to come in and say hello to your video.
I thought you were helping them.
You're fine. You're fine. Okay, so deviations from ideal behavior. Remember that that's going to be at high pressure and low temperature. When we talked earlier today about about how real gases don't follow that kinetic molecular theory, we said that they really don't follow it based on assumption number 2 and number 3. Assumption number 2 was about how we assume that they have negligible volume. But that's not true because we actually do have to take into account that they do have a mass and they will have some type of volume. So that's one of the ways that they deviate. Another way that they deviate is that at these really high pressures and at low temperatures, they will have attractions and repulsions. And so because of that, because they do attract one another and because they do have a finite volume, that's what makes them real gases and that's what makes them deviate from ideal behavior. So at high pressures, gas volumes tend to be slightly greater than predicted by the ideal gas equation. And then another reason, like we said, for non-ideal behavior at high pressures is because the attractive forces between the molecules are going to start to come into play. At a very high pressure, then that means the molecules are bouncing, molecules are moving around very, very quickly. So there's a short intermolecular distance that could be found when those molecules are going to be really crowded around one another. So because of that, at those high pressures, these attractive forces are going to lessen than the amount of collisions that would happen with the wall of the container. And that's just because these attractive forces, if I'm looking here in the real gas, they're going to attract each other more, so they'll bounce more among one another than they're going to with the actual container. So in a real gas at very high pressures, I actually have a decrease in pressure in a real gas because of these attractive forces. If we're thinking about temperature, then the temperature determines how effective attractive forces between gas molecules are in causing deviations from ideal behavior at low pressures. So as a gas cools, the average kinetic energy of the molecules end up decreasing. And this drop in energy means that the molecules do not have the energy needed to overcome that intermolecular attraction. So the molecules will more likely stick to one another, so I have that, and we do not ever really think about that in the ideal gas behavior at all, but real gases will do that. They'll try to stick together and instead of bouncing off one another and then continuing to hit the container and continuing to have those perfect elastic collisions. So at really low temperatures, I can think about how gases will become sticky and then how they don't follow that elastic behavior and elastic collision condition of the kinetic molecular theory, okay? 2 more slides and we are done. So there is a correction for the non-ideal behavior. We call this the van der Waals equation. Van der Waals equation is not anything that's given to you. I think they just want you to know about it very in general. So we can correct for any type of high pressure or low temperature, and we'll use that with the van der Waals. So we adjust it, and it's this equation right here. So the van der Waals equation is this. This looks very, very overwhelming, and that's okay. But again, all it is just correcting for the accounts of attractive forces as well as molecular volumes. You're fine. So let's talk about what these things mean. So A here and B are just going to be an experimental value that I have to determine. A is a measure of how strongly the gas molecules are going to attract one another, and then B is going to represent a measure of the finite volume that's occupied by those molecules. So A and B, again, are just experimentally determined, and I think that all we need to know is that A and B generally increase with increasing molar mass, okay? So van der Waals equation, if I had to find an A and a B, they may ask you a relationship that just says, what would happen to A and B if molar mass was increasing? And A and B will generally increase with increasing molar mass. Larger, more massive molecules tend to have larger volumes, and so they tend to have greater intermolecular forces. So we have to account for that, and by doing that, A and B just become larger. So this is just a way to show how a gas will actually behave based on it being a real gas instead of just an ideal gas. But again, I'm just throwing this in here just because that way you're exposed to it. You're not tested on this. If I do test you on this, it's not going to be anything about, you're not tested on this on the AP test. But I do want you to know conceptually, I can correct for real behavior deviating from ideal behavior by using this van der Waals equation. Okay? And we're not doing that because that's just plugging in things into the van der Waals, but you're not tested on that. So, end of slides, we're done with chapter 10. When we get back from Thanksgiving break, we're going to do some FRQ practice for chapters 5 and 10. We'll do some review also and go over the answers to the multiple choice questions. And then at some point next week, we'll start chapter 11, which is about liquids and then intermolecular forces. All right, I hope you guys have a really wonderful Thanksgiving break, and I will see you on Monday. Bye.